Previously, we have already discussed something about calculation of fixed moments for a continuous beam by using either three-moment theorem and whatnot. But now, this time we are using another method for calculation of the fixed moments at the continuous supports. This method is known as moment distribution method. This method is known as moment distribution method. I am first of all considering a continuous beam of span AB, BC and CD with different boundary conditions, with A is fixed, B and C as a continuous supports, and C the end support, it is a simple support. For starting this problem by moment distribution, what we have to do? First of all, separate each span AB, BC and CD, just with all the loadings which is already given over here. And as we have already studied something about the fixed moments for the point load as well as for the uniformly distributed load over the entire span, find out the fixed moments MFAB and MFBA like this. This is anti-clockwise, this is clockwise, this is taken as negative, this is taken as positive. Then which is nothing but WA square by 12 for uniformly distributed load. Now we will go for this BC. Again, this is anti-clockwise moment, this is considering the fixed just now. Consider each and every span as a fixed one and take the loading and draw it separately and find out the fixed moments at B, C and CB. It is WAB square upon L square. L is over here, is now number 4. So MBC is equal to WAB square upon L square. This is negative. This is positive, WAB square upon L square. Similarly, this also for CB, I have also CD, sorry, this is also taken separately like this and found the fixed moment for C and D, WAB square upon L square. These are the moments. Now you can see here, this is the negative bending moment, this is positive bending moment, this is negative bending moment, this is positive bending moment, this is negative bending moment, this is positive bending moment. AB negative, BA positive, BC negative, CB positive, CD negative and DC positive. Now, going for the next part, I have taken this beam over here like this. Now what we have to do? We have to first of all calculate the stiffness of the intermediate supports. Stiffness of intermediate support. From here we look towards A. If it is fixed, then stiffness of BA is 4EI by L. If that would have been simply supported, then it will be 3EI by L. Here I have taken as 1.5, this is I, this is I. Because this span is more, so I have taken the moment of inertia more, the section is more. So stiffness of BA is equal to 4EI upon L. I is 1.2, here I have written 1.4, but saying it is 1.2. I just confirm it is right, this is 1.2. Similarly, when I go for BC, BC it is 1.2, that is 0.8. So it is not 1.5, but it is 1.2. It is taken as 1.2, not 1.5. So 4EI by L, it is 0.8. Similarly, stiffness for BC. Now, one thing is there. When this another support is there, which is called as a continuous support, which is also called as a fixed support, and this will also be taken as 4 EI by L. Stiffness of CB, again this is next support is there, so it is again taken as 4 EI by L. But when I am approaching towards the FCD, it is 3 EI by L. It is 3 EI by L. Because the last end is simple supported and stiffness will be 3 EI by L. Then I have calculated all the stiffnesses, that is for BA, BC, CB and CD. Just see. This is for BA, this is for BC, this is for CB and this is for CD. One thing, this also called as a distribution. Then we will calculate the distribution factor also. And now just to calculate the distribution factor, what we have to do, distribution factor is to be calculated by stiffness of 1 upon stiffness of the this plus this. Suppose I want to calculate the distribution factor for BA, then stiffness of BA upon sum of stiffness of BA plus BC. I have mentioned over here. Distribution factor for BA is equal to stiffness of BA upon stiffness of BA plus stiffness of BC. Similarly, when we come across over here, stiffness of CB is equal to distribution factor for CB is equal to stiffness of CB upon stiffness of CB plus stiffness of CD. Just right. I have seen over here, when distribution factor for CB, stiffness of CB upon stiffness of CB and stiffness of DC. Actually, it should be taken as not BC, but it should be taken as CB for convenience, because it is one and the same thing still. We should write this as CB instead of BC. Because we have already taken CB over here, so this will also be taken as CB. So we will find 0.44, here it is 0.44, here it is 0.56. One thing is there, that under any circumstances, the sum of the two must be equal. That is equal to 1. Not equal, sorry. Sum of the two distribution factor must be 1. Similarly over here. So if you can calculate 1, that is if you will find out the value of 1 at 0.44, this can be calculated 1 minus 0.44, that is 0.56. Similarly like this. Once the distribution factor is there, then we will prepare a table and straightway come across how to calculate the final moments, that is the hogging bending moment. In a table, first of all the joint. How many joints are there? A, B, C and D. 4 joints are there. 4 joints are there. So A, B, C, D, there are 4 joints. Then member, starting from AB, BA, BC, CB, CD and DC. Now fixed end moment we have already calculated over there. Minus, plus, minus, plus, minus, plus. Now, we know that when the final support is there, that we have already seen over here, we have also seen over here also, final support, that is D support, is the end support and it is simply supported. So, the moment at that point will be 0. Moment at that point will be 0. So, actually here, when we have make the distribution so far, then it will be plus 3.75. So that is to be kept at 0. So what we have to do? We have to make it 0 minus 0.375. And this is to be carried over to the next support, but carryover factor is always taken as half with the same sign. Same sign, that is minus 1.87. Now, after the reality of this support has been carried out and we are getting, then make this, bring it down over here, bring it down over here and all the add over here, and this will be your the initial moment. This will be your initial moment of minus 60 plus 60 minus 7.5 plus 22.8 minus 5.6 and 0. But one thing we have to know, that when we are talking of the moment at any point over here, suppose I am talking about this B, moment at this must be equal to moment of this. We have also seen the moment at this must be equal to. So we have to make the calculation in such a manner, the moment for BA must be equal to BC. If this is clockwise plus, then this should be minus with the same value and change in nature. This is plus, BA is plus, BC must be minus, but magnitude must be same. Till that don't happen, we have to make the iterations to be carried on. Now, after this, now see the difference between the two. BA is plus 60, BC minus 75, minus 7.5. Find out the difference. And the difference is to be distributed according to the distribution factor with a change in sign. Because this is 60, this is 75, this is to be reduced, this is to be increased, just to make the balance. Because we have seen that BA equal to BC. So this is to be decreased and this is to be increased. Finally, it should come to the same thing. Now this is decreased by the distribution factor. So what we did, this minus this multiplied by this 0.44, we change in sign, substitute over here. And this minus this much will be distributed like this. Similarly over here it is plus 22.5, this is minus 5.62, difference between the two, multiplied by one of the distribution factor, and rest of the things is to be placed over here. This is to be carried out over here, this is to be carried out over here. Then we have to make the summation like this. We have to make the summation of right from here, because this has already been carried out up to this. Initial moment is up to this only. So we have to start from here and here, write the final moment at A. Write the final moment at BA. Write the final moment at BC. Write the final moment at CB, CD, and finally if you are carrying out again, it will be 0. So put it always 0 because it is simply supported, and you will find this is negative bending moment. That's over and all. Once we can find out this negative bending moment, which is already shown in red, then this is WA square by 12, WAB by L, WAB by L. Draw the sagging bending moment diagram. Superimpose over here negative bending moment of hogging bending moment diagram, and this diagram you are already aware in case of the 3-moment theorem you have seen. Then this will give the maximum negative, this will give the maximum positive, again this will be negative at B, positive here and positive here. This way, once this is known, then as usual find out the value of RA, RB, RC and RD. Once the reactions are known, draw the shear force diagram that completes the moment distribution. One thing it is to be kept in mind. We know that finally when D is simply supported, the moment is to be kept 0, 0, 0, 0 throughout. Of course, it is to be carried out, but if we will carry it again, we will have to make it minus 0 and we have to bring it back again. So better it is not to carry over, not to carry this on this side, and matter ends. So what we have to do is, if it is something is there, don't carry it out. Don't carry over here, because this is already finally it is 0. In some of the books, what they are doing, they are just carrying half the over here and again changing the sign, again bring it over here. Every time the process is a lengthy process, unnecessary waste of time. It is better to go in this way. Once we put the 0 over after initial moment, see, no moment should be transfer over here, and when it is the end, A is fixed, now always finally the carryover is to be carried out at the fixed end. And once these negative bending moments, the hogging bending moments are known, this will be drawn like this. Thank you very much.